So we tried like this learning rate, that learning rate. We looked at the behavior bouncing back and forth and stuff. Maybe it's better to try a bunch of learning rates systematically, record the answers from each one, and then plot that. So here we're telling it, give us a bunch of learning rates, starting at this, stopping at that, and do 50 steps from there to there. That's what the linspace command gives us. If we wanted to specify the step size instead of the number of steps, we would use a range. We're going to use the same number of steps as above. We're starting at 0, 0, just like we did before. And we're making room here to save the answer we get from each of these different learning rates. So we do a list, we run steepest descent with whatever learning rate, and save the final value of the function values into our list of function values that we got. And we're making a copy of it to stay safe. And then we're doing it again at 40 steps. I think before we were using 500, right? Etc. And now we'll make a plot of it. And so at 500 steps we got the blue here, and at 40 steps we got the red. So I'll give you a question to think about. What is this graph telling us, and what is the best learning rate to set? Pause the video if you need to and think about that. Okay, welcome back from pausing. What I see is that, boy, if you choose a learning rate that's too high, your final function value after 40 steps or 500 steps is up in like 10 to the 8th, 10 to the 17th, and we know the best function value here is 0. So you do not want to choose a learning rate that's too high. Your optimization will just end up running away, diverging. If you choose an optimization rate that's fairly low, well, you won't get as good an objective function value as if you choose something that's in the middle, but you don't really know where the middle is until you try something like this. So you might be saying, well, why would I run this on my model to find the best learning rate? Because I might as well just run the model, right? What you can do, though, is like take a small sample of the data, run this kind of trying different learning rates on that, and then once you find the best learning rate, then go run it on your full set of data. And the key there is you need something whose typical gradient component size doesn't change when you use more data. So if you're doing sum of squared errors and you go from 100 data points to 1,000,000 data points, you're adding up a bunch more squared errors, you're going to get a much larger values, and so your learning rate would need to be much smaller than when you tried it on just 100. But if you're using mean squared error, that doesn't systematically get bigger when you include more data points. So that's why we're using mean squared error in this notebook. The other big question here is, what's the best learning rate to choose? The one that gives you the smallest function values here? Oh, we can also see when I'm taking more steps, I end up with a lower function value after 500 steps than at 40 steps for most of these reasonable values here. But what's the best learning rate to choose? Well, you might say the one that gives me the lowest final objective function value, right? Which is good in the short term, but if you get it a little wrong, what's going to happen to your objective function value? It's going to be terrible, right? Your algorithm's going to diverge. So this is a case where choosing something that's a little safer, giving up a little bit on what you expect for the final value, with the benefit of having a lower risk of something going really bad, is probably a good idea. So here we'd probably choose things in this range rather than right close to the edge of the cliff here.